Welcome to the AP Physics video lecture on momentum and energy. This problem. Scenario. A 4.0 kilogram block is initially at position x equals to 0 and in contact with an uncompressed spring with the spring coefficient k equals to 2 of negligible mass. The block is pushed back along a frictionless surface from position x equals to 0 to x equals to negative 5 meters. The block is then released. Right at x equals to 0, the block has its maximum velocity, then enters a rough part of the track and eventually comes to at rest at position x equals to 15 meters. The coefficient of kinetic friction of the rough track is mu equals to 0.25. The question: what is the potential energy U of the block spring system? Answer: the formula for the compressed spring potential energy is 1/2 K delta X squared. Delta X represents the compression length. I plug in the value 5. Even if you plug in negative 5 for delta X, you will still get the same answer because it's going to be squared. Plug this in, you should get the value of 25 joules. This is how much energy the system has when the spring is being compressed by the block. What is the maximum velocity of the block? After you let go of the compressed spring, the spring is going to shoot out, releasing that block. All that spring potential energy is now going to be converted to kinetic energy. Ug is going to be equal to K. That's the spring potential energy is going to all go into its kinetic energy. That is based on the conservation of energy. Kinetic energy equation is 1/2 mv squared. So you're essentially plugging this in and solving for v squared. You can do the algebra here. The 2's and the 1/2 here cancels. Then you would just take the square root to solve for v. You should get velocity equals to 5 meters per second. So the question is, why does the block stop at v1 equals to 0? Why does it stop roughly when it goes to that track there? The reason why is because it goes to that rough part of the track. The force of friction does work on the block, taking energy away. So you can say that all the kinetic energy is transferred out of the system in the form of thermal due to the force of friction. So this is what an energy question looks like, and now it's going to be connected to its momentum. It's the same scenario. You can be asked how much work does the force of friction does on the block to stop it? Well, the work can be defined by the change in kinetic energy, or you can do force of friction times the distance. Well, you know that the distance is 15 meters, but you still need the force of friction. So, how are you going to get the force of friction? You can find the force of friction using the formula for the change of momentum. Force of friction, or any force, times the change in time is equal to the change in momentum. That is how momentum connects to the force and the work. The issue here is that you will need time here. So, to do that, you have to grab your kinematics equation. Your kinematics equation that is going to be used here is the quadratic one. There are some terms. The acceleration here goes to 0, so it can be simplified into delta x, which is the distance traveled, is equal to the initial velocity times time. So we know that the total distance traveled is 15 meters, and we know that the initial velocity that we got from the last part of the question was 5. So 15 equals to 5t. Divide by 5, you get t equals to 3. Now you have the time. Now you can now plug it in to the equation in the middle for the momentum. What I did here is I divide delta t to both sides, so I get force of friction is equal to the change in momentum divided by the change in time. I have the top part. The top part is going to go to 0 because the final is at rest. Then we have the initial here. So the MV1 goes to 0. This goes to 0. Then you're left with the mass, which is 4, times the times the initial velocity, which is 5, divided by 3. That gets you negative 6.67 newtons. The negative just indicates that the force was in the opposite direction, so it was towards the left. So the negative just tells you that this is to the left. Okay? So we can just plug it in here. So plug in that negative 6.67 newtons into the work equation times 15. You get the work is equal roughly to 100 joules. The negative here just indicates that energy was taken out of the system. That's why it was negative. All right. So here, this gives you a combination of how momentum is used in relationships to energy and kinematics. This scenario of the block should give you an indication of how energy and momentum are related. This leads us into our idea of collision. Collision, in its basic form, can be seen as two particles that are moving freely until they get closer to one another. Then, for a short period of time, they exert strong force on each other until they move apart and are freely to move again. There are several types. What you need to get from this slide is seeing how their momentum and energy are related. The first type of collision is called an elastic collision, sometimes called perfectly elastic collision. This is when two objects come together, they hit, then they separate. The momentum is conserved and the kinetic energy is conserved. The momentum is conserved in the sense that the velocity and the masses remain the same before and after the collision. They might have different values, but the total momentum before and after are the same. Nothing is lost. The system is essentially closed. An other type of collision is called an inelastic collision. So there's a red part here, IN, that is placed here. How that changed, you're going to notice right here, it's in red. The momentum is still conserved. However, kinetic energy is not conserved. That's why it's in red here. It indicates the inelastic collision is not conserved when it comes to kinetic energy. So during the collision, when it hits, it's like that. So why? In the microscopic level, at the atomic level, the collision between these two objects, the kinetic energy is changed to some form of energy like thermal. So them hitting on the smallest scale, energy is being lost to heat or in the form of heat. That is why an inelastic collision is not conservative. So the difference between an elastic and inelastic is the kinetic energy, if it's conserved or not conserved. In real life, all collisions are most of the time inelastic because you do lose things to thermal energy. Lastly, the last type of collision is called a complete inelastic collision. The complete part comes from them being stuck together. So, in this case, it behaves the same thing as before. Momentum is conserved, kinetic energy is not conserved because the two objects sticks together after the collision. In inelastic collision, they stick together briefly and they lose it to thermal. a completely inelastic, they collide and they still get stuck together at the end. The reason why is because at the microscopic level, at the atoms, the energy is used to stick the atoms together. So the energy from the kinetic energy is transformed to create the bonds to link the two objects together. Therefore, energy is lost. So these are your three types of collisions. These idea of what is conserved and not conserved are very crucial for you to justify and explain the equations that you use. So there you go. This is everything that you need to know when it comes to connecting momentum and energy together.